In this lecture, we're going to talk about the small rotation solution to the Bloch equation, small rotation pulses, and large flip angle two-dimensional pulses, and specifically the linear class of large tip angle RF pulses. So up to now, our multidimensional selective excitations have been restricted to small flip angles. We haven't pushed them past that regime. So in this lecture, we're going to learn how to design pulses using under what conditions we can design pulses using the small tip approximation such that they will scale to large flip angles without incurring distortion due to Bloch equation nonlinearity. To get there, we first need to derive an approximation to the Bloch equation for small rotations. And what we're going to do is we're going to segment a pulse into a series of small rotations and show that when we concatenate those all together, we still get the profile that we want. This is going to be like a small tip angle equation derivation, but without the assumption that the magnetization is initially along the plus z-axis, or along the longitudinal axis. So we start with the Bloch equation without relaxation, where the incremental change in the magnetization is equal to the rotation matrix containing the gradient and RF terms multiplied by the current state of the rotation. We're going to assume here that the gradient, which could have gx, gy, and gz components, is a function of time, so is the RF, and then position is x, y, z, r. And as before, when we were talking about SLR pulses, we can rewrite this Bloch equation as the incremental change in magnetization is equal to the rate of rotation omega times a normalized vector n about which we are rotating times the rotation matrices S times the current state m, where again omega is the rate at which we are rotating, and it depends on and is the norm, the Euclidean length of the instantaneous total magnetic field. N here is the normalized vector about which we are rotating, and S is the collection of rotation matrices, 3x3 rotation matrices, for rotations about each axis. So if you recall from the SLR lectures, this is called the SO3 representation. In SU2, this corresponds to the incremental change in the spinner is equal to I square root of minus 1 times the rate omega over 2 times n dot sigma, where these are the 2x2 rotation matrices, as we defined before, times the current state of the spinner, where omega and n are the same as they are in the 3x3 case, and sigma is the collection of these 2x2 rotation matrices. Substituting omega and n, we can get this 2x2 equation, and then recall further that the spinner is the vector containing alpha and beta, so we can substitute that in for psi here, and we arrive at this 2x2 Bloch equation. So now we're going to do what we haven't done before, and we're going to express the Bloch equation in terms of alpha and beta. So if we expand this out, we get that the time derivative of alpha is equal to I times gamma over 2 times g vec of t dot r times alpha plus I gamma over 2 times b1 complex conjugate of t times beta, where b1 of t here is equal to bx plus I times by. And then the time derivative of beta is equal to I gamma over 2 times b1 of t times alpha minus I gamma over 2 times g vec of t dot r vec times beta. Okay, so here's where we're going to make the small angle approximation. We're going to assume that the rotation angle phi is small at this instant, and so beta, which is equal to minus I times nx plus I ny times sine phi over 2 is approximately 0. That allows us to solve the alpha equation, because now the alpha equation is approximately I gamma over 2 g vec of t dot r vec times alpha, since the beta term vanishes. So alpha is some yet unknown constant times e to the I over 2 r vec dot gamma integral from minus infinity to t, g vec s ds, so s is the integrand here. And this then is equal to c times e to the minus I 2 pi r vec dot k vec of minus infinity to t, that is the excitation k space from minus infinity up to t. Now the constant c here has to be equal to 1, since for a 0 rotation, alpha has to be approximately equal to 1. So alpha of t overall is equal to e to the minus I 2 pi times 1/2 times r vec dot k vec of minus infinity up to this instant t. And now we can use this solution for alpha to further solve for beta. So the time derivative of beta, without any approximation, is I gamma over 2 times b1 of t times alpha minus I gamma over 2 g vec of t dot r vec times beta. And we can pull the terms containing beta over to the left-hand side, and we get beta dot, again the dot stands for, it denotes the time derivative, plus I gamma over 2 times g vec of t dot r vec times beta. That will be equal to I times gamma over 2 times b1 of t times alpha. Then we can substitute our solution for alpha and get beta dot plus I gamma over 2 g vec of t dot r vec times beta is equal to I gamma over 2 b1 of t times e to the I over 2 gamma times r vec dot integral from minus infinity to t g of s ds. So now we're going to do something interesting. We're going to multiply both sides by alpha again. Here it's acting as an integration factor that simplifies the solution. So what we're going to do is multiply both sides by alpha, and then the left-hand side becomes a chain rule, in that you take the derivative of one factor times the original other factor, and then the derivative, and then leave the one factor alone and take the derivative of the second factor. So I'll just write it down here and then explain it. So if we multiply on both sides and apply this simplification, what we will get is d dt of beta times e to the I gamma over 2 times r vec dot integral from minus infinity to t g vec s ds. Okay, that's the left-hand side now. And the right-hand side, if we multiply it again by alpha, is going to be equal to I gamma over 2 times b1 of t times e to the I gamma r vec dot integral minus infinity to t g vec of s ds. So the right-hand side, all that happens is we get rid of the 1/2 here in the exponential. But on the left-hand side, multiplying by alpha allowed us to combine these two terms and pull out the time derivative. And you can see that by working backwards. If you were to take the time derivative of this, it would be derivative of beta times this term left alone, which is what you would get here after multiplying by alpha. And likewise, if and then that would be added to beta left alone here times the derivative of this guy times alpha, which is the derivative of this guy is this, and you'd have an extra alpha term because you multiplied by alpha. So it all checks out. Okay, now we can integrate this, and we will get beta times e to the I gamma over 2 r vec dot integral minus infinity to t g of s ds, and that guy is equal to I gamma over 2 integral from minus infinity to t, b1 of t, sorry, b1 of tau, we're going to use tau here, as the integrand, b1 of tau, e to the I gamma integral from minus infinity to t, sorry, to tau, up to tau, g vec of s dot r vec ds, and then coming back down, d tau. So, if we multiply by alpha conjugate on both sides, we can get the solution for beta alone is beta of t is equal to I gamma over 2 times e to the minus I over 2 integral from minus infinity to t g vec of s ds, sorry, there should be an r dot in here, that's alpha conjugate, times the integral from minus infinity to t, b1 of tau, times e to the I gamma, integral from minus infinity to tau, of g vec of s dot r vec ds, and then coming back down, d tau. Okay, and with a little more manipulation, you can show that you can substitute in the excitation k-space definition here and obtain beta of t is approximately I times gamma over 2 e to the minus I 2 pi times r vec, 2 pi over 2, r vec dot k vec of minus infinity to t times integral from minus infinity to t b1 of tau times e to the I 2 pi times k vec running from tau to t, where the integral inside k vec runs from tau to t, dot multiplied with r vec d tau. And alpha of t has the expression we showed earlier, e to the minus I 2 pi over 2 times r vec dot k vec of minus infinity to t. So as a sanity check, we can see whether we can recover the small tip approximation from this. So recall that mxy, if all the magnetization is initially along z, then mxy after an RF pulse is 2 alpha conj beta. And substituting in the expressions we came up with on the previous slide, we get 2 times e to the minus I 2 pi over 2 times r vec dot k vec of minus infinity to t, complex conjugate, since alpha is complex conjugated, times I gamma over 2 times e to the minus I 2 pi over 2 r vec dot k vec of minus infinity to t, and then times the integral from the previous expression for beta. And the key here is that these two are conjugates of each other. Since this guy's complex conjugated, its minus sign is going to turn into a plus, and it's going to cancel the phase of this guy. So it vanishes, and what we're left with is I times gamma integral from minus infinity to t b1 of tau e to the I 2 pi r vec dot k vec from tau to t d tau. So this is the same as the small tip angle equation, and we can think about the small tip angle equation as being a special case of the small rotation solution where the magnetization is initially along the z-axis. Okay, another important special case of the small excitation solution is when the gradients integrate to 0. And then the B1 is furthermore conjugate or Hermitian symmetric. So we have to have these two conditions, that the gradient waveforms integrate to 0, and B1 is conjugate or Hermitian symmetric. In that case, we have what's called an inherently refocused pulse, and this is an important special case of the small excitation solution. So for example, a 1D pulse that satisfies these requirements could have gradients that are balanced trapezoids. So here, the negative lobes sum together to cancel out the main lobes, so you get 0 total area. And then the RF could be this split and mirrored waveform. Okay, so what we'd be doing here is we'd be starting in the center and moving negative. This would be segment 1. This is segment 2, and this is segment 3. This is 1, 2, and 3. We'd be moving this way during segment 1. Then during segment 2, we would go back. I'm drawing them slightly offset from each other just for illustration. So this is 2. And then on the third part, we're going to go back to 0, go back to DC. So this is 1, this is 2, and then this is 3. So because we have symmetric k-space weighting about k equals 0, and we start and end at k equals 0, this is an inherently refocused pulse. Okay, and furthermore in this case, our expressions simplify. Since k from minus infinity to t at the end of the pulse is 0, then that means that alpha is equal to 1. And beta also simplifies, since the alpha term out front is equal to 1. And furthermore, we can say that this integral is going to be real. That is real valued. So why is that? Well, it's because of the Hermitian symmetry of the RF waveform in the trajectory that we cover with the gradients. Since a Hermitian symmetric Fourier transform corresponds to a real valued pattern. So if beta of t produces a Hermitian symmetric weighting, and k of tau comma t is symmetric, then the integral is real, and beta is purely imaginary because of the square root of minus 1 out front. Now recall that beta is equal to minus I times nx plus I ny times sine phi over 2. This is another definition of beta. So if beta is purely imaginary, as derived above for the self-refocused pulse, then that corresponds to a rotation about x. That is, nx equals 1 and ny and nz are 0. And this rotation is equal to 2 arc sine of minus I times beta. Now we know that for small angles, arc sine of x is x. So beta is really equal to the flip angle pattern under this small excitation self-refocused case. So we can simplify it down again to get this expression for the flip angle pattern. So what this means then is that the rotation angle is the Fourier transform of the weighted k-space trajectory, the pattern of rotation angles. Sorry, I should say the rotation angle pattern is the Fourier transform of the weighted k-space trajectory. And this holds for any initial magnetization m naught. We didn't assume anything about m naught in arriving at this. So, and that's because overall that's because we solved for a rotation, not for magnetization. We have yet to apply it to any state of magnetization. So the significance here is that large tip angle pulses can be built up from a series of small rotations if they're performed around a common axis, which here is x-axis. And there's two important cases that we'll talk about. The first is one-dimensional spatially selective rotations for spectral spatial inversions and spin echo pulses. And then the second case is two-dimensional and three-dimensional rotations built up in spatial frequency space. So the canonical example of case 2 is a spiral inversion or spin echo refocusing pulse. So let's say we have a gradient trajectory that looks like this. So the dashed lines here are gy, and the solid are gx. They trace out a k-space trajectory here on the right. And it's a pretty cruddy drawing here, but in reality we can approximate an n-turn spiral trajectory as a series of n circles that are traced out in k-space one after the other, plus blips up and down from DC. So the outermost turn, for example, you could say that you started at DC, blipped up, went around and up here, and then came back down to DC. That is then added to the rotation that you obtained by going out a little bit less far, going all the way around, and then coming back to DC, all the way down to the innermost turn, where you blipped out just a little bit, went all the way around the circle, and then came back home. So the jth turn then produces some flip angle j, phi sub j, which is a function of position, and the time t sub j, where you integrate the RF waveform in the window corresponding to when you traced this circle, and the k-space trajectory for that circle as well. Now, we're assuming here that all these rotations are Hermitian symmetric in k-space, and so then they're all about the same axis and they add together. Again, this is because this is a requirement for the linear class for this to work out. So the total rotation then is equal to the sum of the individual rotations over the number of turns in the spiral, capital N. So the individual rotations are phi sub j, r vec, comma, tj. And that's equal to j equals 1 to n, integral from minus integral of t sub j minus 1 to t sub j, gamma b1 of tau e to the I 2 pi k vec of tau comma tj dot r vec d tau. And we can just concatenate all of these into one single integral and restore back the original small tip angle equation, which is integral of 0 to t from 0 to t of gamma b1 of tau e to the I 2 pi k of tau comma t dot r. So all of this is just to show that the original small tip angle equation applies here when we're thinking about concatenating all these rotations. When we think about this as a series of self-refocused small rotations, what we get is the same thing as the small tip angle equation for the pattern of flip angles that's produced by the pulse. So then the rotation produced by a large tip angle pulse is the Fourier transform of the weighted k-space trajectory, provided, so I should put a comma there, comma, provided that the trajectory can be decomposed into symmetric segments about the origin, they have to be symmetric again to get Hermitian symmetric k-space weighting. And furthermore, that the RF pulse produces conjugate symmetric weighting when it's applied simultaneously with that trajectory. Here are three trajectories that satisfy this requirement that they can be decomposed into a series of small rotations, self-refocused small rotations centered on the middle of k-space. So the first and most practical one is the spiral trajectory, as we've seen before several times. Another one is the Lissajous trajectory. And finally, the pedal trajectory, which is similar to a rosette, where you have an oscillating term here, and then you basically multiply one slowly oscillating waveform, which moves you around this way, with a faster oscillating term, which gets you these tight bends. Here's an example of a spiral spin echo pulse. Here's the RF pulse waveform, similar to what you've done in the homeworks. Here are the gradient waveforms. Here's the mx multiplied by 50. We see nothing. Here's the my. So we produced a nice rotation along my. And here's the magnetization profile as well. So it did a really nice job. We didn't get any distortion due to Bloch equation nonlinearity. This pattern looks the same as it would if we'd used this pulse for just a 30-degree flip angle. Here are the patterns zoomed in. Note the y-axis here. So mx is less than 0.005 and my is about perfect.